Great to have you back again. In the previous presentation, I introduced to you the methods of fast tracking and crashing. In this presentation, I will show you how to apply activity crashing on a project. We're going to apply the principles of crashing, and we were going to create a network diagram, a project, and we want to know what is the relationship between the duration of the project and the cost of the project. Because every time we crash activities, the cost of the project increases, and we want to know when our customer would say, okay, I want to have a project finished in a certain time period. I want to know what we estimate that our project will cost. And once we know the cost of the project, we can basically calculate what the sales price to the customer would be. We can also use it for other applications when we see that we have problems. What is the effect of the crashing? But in this example, we just look at the relationship between time and cost. Now, let's have a look here when we are looking at the application of crashing on a project. Like I said before, we want to find out the relationship between project duration and cost because we want to know what is basically the cost of the project if we have to reduce the size of the duration of the project. What are the assumptions? First of all, the cost and the duration of all activities is known in both situations. So we know the duration and the cost both in normal and in crash situation. The relationship between duration and cost is linear. When we look at the crash cost, the relationship between the time duration of an activity and its cost, that is a linear relationship. It's not necessarily true in reality. We could make different models, but we keep it simple here and we just assume that this is linear. And I'm convinced that in most of the possibilities that we have, except in some very special cases, that we won't have a problem. Now, we only consider the cost of the activity. So like in the previous example, we were looking at the project management cost, we were looking at eventually fines and rewards. We're not looking at those elements. So we are no fines, and the final result, like I said, is that relationship, the time and cost relationship. Let's have a quick reminder about the crash cost. When we look at normal and crash duration of an activity, we have the normal duration, the normal cost, the normal the crashed duration and the crashed cost, which we have here. And we said that the relationship is in fact linear. And based on that, we can calculate the crash cost per period, which is given by the relationship or by the fraction crash cost minus normal cost divided by normal duration minus crashed duration. And that's what we're going to apply. And in the first step, what we're going to do is to calculate the crash cost of all the activities that we have. Let's look at the example the project that we are going to discuss here. And here we have a table where we have the activities, the predecessors, the normal and the crashed parameters, and then I put there slash per period to save some space. This is basically the crash cost per period that we're going to calculate. And we start with, of course, activity A. The formula is the same. Crash cost per period is the difference in cost divided by the difference in duration. And for the first period, we look at this, and what do we see? We see that the normal duration is 5, the crash duration is 3, which means that we can crash activity A with 2 periods, and the cost goes from 5K to 6K. Now, the crash cost is always higher than the normal cost. Otherwise, we have a problem and there must be something wrong. So basically, when we calculate this, we find that for this activity, we have a crash cost per period of 0.5K, whatever the monetary unit is, and can put it here in the first rectangle. So that's basically our first calculation, and we can continue those calculations for B and C, so we find respectively 1K and 2K. But now I want to look at activity D. And when we look at activity D, there is something special, because what do we see? We see that the normal and the crash durations are the same, and the crash cost and the normal cost, of course, are the same also. So let's have a look at the formula. The formula is still the same, but when we calculate this, we find 0 divided by 0, and this is not defined in mathematics. So basically, we cannot say, which is a mistake which is done by many people, and I've seen it many times. They say the crash cost is 0. Now, that's not true. The crash cost is 0. Basically, what we know here, we cannot apply crashing on this activity. So whatever we do, if D is on the critical path, we cannot crash D, and we have to keep that activity as it is. So we have to put here not applicable for crashing. Can continue with the others, and we find all the other crash cost per period, and we see that we have for E 1.5K, for F 3.5K, for G 1K, and for H also 0.5K. Now, what are the next things we have to do? The next step is draw, let's say, the precedence diagram, and of course we have to order the activities from low to high. We want to crash, we want to have the lowest cost possible, so whatever we do, we always start from the lowest crash cost per period. Now we have to identify the activities on the critical path, because activities that are not on the critical path, when we crash them, they will not lead to a reduction in duration of the project. And that's not what we want. We want to crash the project, and we have to use the activities on the critical path, because reducing the critical path is done by reducing the duration of its activities. And once we have the critical path, we select the activities that we have to crash, and we start with the activities on the critical path with the lowest crash cost. Now here you have to be very careful, because we may start with one critical path and we start crashing. We may have critical path convergence, which means that the slack of the non-critical paths is reducing. They come closer and closer. And at a certain moment, the critical path can change, or we may have at a certain moment two critical paths. And in order to crash the duration of the project, we have to reduce all the critical paths. Now let's have a look how we go from here. So the first step, I already said, we have to look at the precedence diagram. We've already drawn this, but let's just have a look at it again. We first start with A. Following A, we have three activities. So A is predecessor of B, C, and D. Now we have E, which has predecessors C and D, F as predecessor B, and G as predecessor D. And the last activity, H, as predecessors E, F, and G. So basically this is the precedence diagram, and on the board we will calculate the critical path. We will use this calculation to find the critical path, early start, late start, and so on. So basically we will find the result of this. So let's go to the board and have a look how this project looks. What are the starting points? What are the different characteristics of all the activities? What is the critical path? And then we will continue with the crashing. The first thing we do is to do the forward pass, and in the forward pass we are going to calculate the start and finish times from left to right. Now we have to look at some formulas that we are going to use, and we know that the early finish of an activity is equal to its early start plus the duration minus 1. The second thing that we have to know is that the start date of the successor is in fact the early finish of the activity, the previous activity, plus 1. So I have to put here early finish, not early start, early finish. So basically when we start calculating, we start from 1 in this method. I have 1 and 5. So basically now here, B starts the day after, or the period after. B, C, and D start at period 6. Now we have 6 plus 7 minus 1 is 12. 6 plus 3 minus 1 is 8. And 6 plus 5 minus 1 is 10. Now F will start at period 13. F 13 plus 4 minus 1 is 16. And now I have E. E has two predecessors. So C and D. And then we have to take the highest early finish time. So 10 plus 1 is 11. Then we have 11 plus 9 minus 1 is 19. And here we have also 11 because there is only one predecessor. 11 plus 6 minus 1 is 16. And we have here basically 20, and we find 27 as end time for the project. When we finish the the forward pass, we have to calculate the backward pass. So we're starting to calculate the late start and the late finish from the left to the right. We're going to say that the late finish of the project is equal to the early finish of the project. So we start from 27, and 27 minus 8 plus 1 is 20. So now we go to the predecessors, minus 1, so we have 19, 19, and 19. And we can continue. Now it's very easy to see. These two are the same, so basically these two have the same 2. 11, so we can go to 10 here. Here we have 19 and minus 6, that's 13 plus 1 is 14. And when we have two successors, we take the lowest number. If we would take 14, we would see that this activity would be late and we would run into problems. So basically here we have 10 and we can continue. So here we have 19. 19 with minus 4 plus 1 is 16. So we have 15 here. And now we can continue. 15 minus 7 plus 1 is 9. 10 minus 3 plus 1 is 8. We have 7 plus 1. 10, and we have those two the same. So this is also equal to this. And now we can, in fact, continue. We have 9, 8, and 6. So the late finish of A is, in fact, the minimum minus 1, which is 5, and we find the early finish or the late start equal to 1. What we have to do now, the last part that we have to do, is to calculate the slack. And the slack is in fact given by the formula late start minus early start, or late finish minus early finish, and those is slack. Now when we look here, we have a slack equal to 0, we have a slack equal to 3, a slack equal to 2, a slack equal to 0, 3, 0, 3, and 0. Now we have to find the critical path. Now the definition of the critical path is the longest path through the network. Now basically what happens here is that we have to find that path. Now what I can say is when the early finish of the project is equal to the late finish of the project, the activities that have slack equal to 0 are in fact on the critical path. If those two are not the same, then the critical path is given by the activities with the lowest slack, even when it's not equal to 0. Remember, there always has to be at least one critical path, and in the worst case, all paths can be critical. So basically, the critical path here is given by the activities A, D, E, and H. And when we calculate the duration of all these paths, we will see that the path A, D, E, H is the longest path because it's equal to 27 periods. Let's look at A, B, F, H. We have 5 plus 7, so that's 12. 16 plus 8 is 24, which corresponds with a slack of 3 because this path is 3 periods shorter. Now we have the crash cost per period in the next step, so we have already calculated these elements here, but what we see is that basically now we have identified the critical path, which is A, D, E, and H. And when we look at the activities, first of all, the activity A has the lowest crash cost per period. We already know the activities from high to low, so now we have to look at the red activities, which are in fact on the critical path. And now we have to select the activity to crash on the CP with the lowest crash cost. Now we can select A or H. Both of them have a crash cost of 0.5K. And what we have to do here is select A or H. Now, I select H to start with. And why is that? Well, when you remember the precedence diagram, H is at the end. So basically, only the calculations of H change, and there is no other calculation that has to be done. So it's a little bit of a lazy logical solution, and we can crash this activity with 3 periods. We will do that on the board, and that's the first step. The other network diagram, the other parameters don't change. So basically, we avoid all the risk of creating a second critical path here. Of course, crashing is rather complicated when you start doing it. There are some mathematical methods that you can use using linear programming and so on to find the optimal solution. But when we draw it, we go through it step by step. And let's do that on the board and see what we basically find after we crash this project step by step and what the relationship between duration and cost of the project is. We finished the precedence diagram like we did in one of the videos before, and now we have the completed overview of the activities, their normal cost, their crash cost, and the crash cost per period. And we see that the critical path is A, D, E, H, which also means that I only have to consider for the first crashing step A, D, E, and H. D cannot be crashed, so we have to make the choice between A, E, and H, and we see that both A and H are the cheapest ones to crash. Now, first of all, we have the original situation where we have 27 periods and a cost of 42K. So that's where we start. Now, what we're going to do, we can crash A or H. Now, when we look at crashing H, we can crash 3 periods. So H, we can crash 3 periods, which would bring our duration to 24 and our cost 42 plus 1.5K. So this will lead us to 43.5K. And why do I select H? Because it's easy, it's at the end, and it only has an effect on H itself. So I put here 5, so I have here 24 and 24. So that's the first crashing step. Now the next crashing step, when we're going to look at it, is in fact at activity A. Activity A, I can crash with 2 periods, so I find here 3 and 3. Now that leads, if I would do the calculation, and I'm not going to do it, you can do it yourself, finally to a reduction here to 22 periods, 22. And what is very important here, when I crash A with 2 periods, we go to 22, and my crash cost or my cost becomes, in fact, 1K more expensive, so I find 44.5K. Now, all the slack of the activities B, F, C, and G does not change in our case. So it's quite easy. We don't have to do so many calculations. What is still remaining? I finished A, I finished H. I still have activity E that I can crash with 3 periods. So we go here to 6 and 3 periods less. So I find 19 here and 19 here. So A, we crash 3 periods. So I have here plus 4.5. That's the total crash cost that we have. So we find here 49K with 19 periods. Now what happens here is that this slack after crashing E would go to 0. This slack would go to 0. This slack would go to 0. This would remain 2. But we have all those critical paths. And if we want to crash further, we have to crash all those critical paths at the same time. And we cannot do that anymore because we have no possibility to crash this path. We can crash this path, we can crash this path, but it won't bring anything. We arrive at the final duration, which is 19 periods. Now, what we can do now, we can crash all the activities. We can calculate the diagram again, but we're not going to do that. It's not necessary because now we see when we crash all the activities, we find a time of 19 with a cost, when we add up all the crash cost of the activities, of 57.5K. Now, what we found here is the overview, the relationship between the duration and the cost of the project. And that we will put in a graph so that we can select whenever we have an agreement on a duration, that we can immediately find what is the cost for doing that project at that duration. After completing the crashing on the board, we find the following relationship between time and cost. 27 periods, the original timing for the project, has a cost of 42K. When we do the first crashing, we go to 24 periods and we have 43.5K. And we continue 22 periods for 44.5K. And finally, 19 periods for 49K. And when we crash everything, we find a total cost of 57.5K. But the duration of the project is not reduced anymore. The only thing we do here with the additional crashing is basically creating more slack for the activities which are not on the critical path. Let's have a look in the graph. So we have the first number, 27, with a cost of 42K. Then we have 24 periods with a cost of 43.5K. And we connect this so we can calculate also the crash cost or the cost of the project for intermediate durations. We continue with 22 periods and a cost of 44.5. Then we go to the final, the shortest duration, with a duration of 19 periods and a cost of 49K. Now we continue with the vertical line where we crash everything, and we see that for that crash cost or for that duration, 19 periods, when we crash everything, we have the duration or the cost of 57.5K. So this is a relationship that can help you finding, in fact, the relation between time and cost. So when you have a certain limit set up, with this information you can determine the basic project cost, add your profit, add your additional costs, and give a price to your customer. So that was it for the activity crashing. It's rather complicated because there are a lot of calculations to conduct, and this is just one example. You can find other examples also on our YouTube channel. In the following session, we will look into uncertainty in project management and project parameters like duration and cost. And we will be looking at what we call the PERT or the 3-point estimates, where we'll calculate an expected duration with 50% probability and a standard deviation so that we can make some assumptions about the probability and the duration and the cost of a project. That was it for this video. I thank you very much and I'm looking forward to seeing you in our next video. Thank you and bye bye.